The next talk is going to be about CernVM-FS with Apptainer Singularity, and this will be given by Dave Dykstra. Just
Right.
pass across to Dave to start his talk.
Great, thank you, Simon. First, I'll introduce myself a little bit. I work at Fermilab, and I'm not the primary developer for either CernVM-FileSystem or Apptainer, but I have been a big contributor to both of them. And I also am kind of de facto person in charge of the operations of the CernVM of CVMFS in the high throughput computing in the grid world. And I'm on the technical steering committee for Apptainer, so one of the 5 people who are responsible for maintaining it at this point, and lead of the security team there. So I'm first going to give a brief introduction to CVMFS. I know it's been discussed in this meeting in previous years, so probably most of you are familiar with it, but maybe some of you aren't. These are some of the best features of it is that the files appear immediately present, so you can do an LS and look and see the files. It looks like they're there on your machine, but they're not actually there until you access them. Then they get downloaded on demand. So this is, and the origin of the files, it can be from anywhere in the world. We can host repositories. Those are called on a Stratum 0. We call that or sometimes a release manager machine where the files are originated. The metadata operations then are done on the client node. And this is also a huge, big win. You don't have to go off to some server to find out information about files. They're all there on the client node. And what they have is, it works by using catalogs that are downloaded behind the scenes, and they list the information about 100,000 files, or usually quite a bit less, but that's about the limit that we like to have in them. Those are SQLite files, those catalogs. And then the files themselves are stored and they're transferred named by a secure hash of the content of those files. And then they are deduplicated and compressed, so you can have the same files published in many different places, even within the same repository. And then they resolved only one file because they're the same file. The catalogs from different places can point to the same file, and they are also compressed during transfer, or for transfer. And the way this works is they're served from a small number of worldwide, what we call Stratum 1 servers, which make a copy of all the repositories. And then they're cached in HTTP proxy caching servers, Squid, it's a recommended one, at each site, and then cached in each client node. So if you start a lot of jobs on the same node using the same code, they'll already be there in the local cache. Or if you start a lot, what's more likely is you start lots of jobs on a lot of different nodes at the same site, then it only needs to be downloaded once from the Stratum 1, and then it gets locally transferred to all the nodes. Then the whole repository is cryptographically verified, the digital signature. And it's very efficient because it's only done on one small file on each repository. Each time a new publication happens, it creates a new signature describing the current state of the repository. And also the larger files, they get broken up into about 8 megabyte chunks. This all happens transparently. And this is helpful for smoothing out the load on the servers so that you don't have nodes trying to download hundreds of megabytes all at once, which can lead to unfair sharing of the servers, especially the squids. And also there's a feature I'm not going to talk much about, but there's an optional external data server mode where you still have all the metadata. The catalog still goes through the standard path, but then the files, the data themselves comes instead of going through the Squid caches. They come from separate servers, which we can distribute geographically around the world. And these are at high capacity network sites. And so each node would load directly from those caching servers. That's for data, as opposed to, tends to be in larger files. And it's also tends to, this is really for partially reused data files, instead of things like the CVMFS is mainly intended for code distribution, and where you start up a whole batch of jobs at once and they all are using the same code, so that you get really very good sharing, very high cache hit rates. Whereas this other mode is more for when we have partially shared files, and not every job in a batch reads the same data, but reads from a set of data. That's what that's for. So CVMFS is also ideal method for distributed containers, especially with use of the sandbox style of files. Now, I'm not going to give an introduction to Apptainer. That's coming by Forrest in the next talk. He's going to be talking about Apptainer and Singularity, but hopefully most of you are familiar with this tool. So the sandbox files, when the files are all unpacked and into a file system. And so CVMFS then has all the advantages of CIF files, these monolithic Singularity image file format files that really made Singularity popular in HPC systems. And probably most of you, since this is really HPC community, I think you're familiar with those. And the biggest thing is that all the metadata operations are moved to the client. And this is what happens with CIF files, and it's a huge performance win, because HPC systems all have these high speed for high performance file systems, which work great for large files. But if you have zillions of small files, as we tend to have with software, all the include files, all the tiny data files, all sorts of scripts, all sorts of things, your download libraries, things get downloaded. Those all, when you have a whole lot of nodes all of a sudden hitting the same metadata server in a file system, those get really slowed down. So people found, running benchmarks, when they started using CIF files in Singularity, the performance was much better than if they were trying to read their files straight off of their high-speed file, the software files straight out of their high-speed file servers. So this is really what I think, this is the main reason why Singularity took off in popularity, because of this performance advantage. In addition, the CVMFS and CIF files, both only the portions of the file that are used. So it's this huge file that you mount on the node, but you don't actually download it until you start accessing it. Same thing happens when you've got this CIF file as you do with CVMFS. They're also cryptographically verified and stored compressed. So it has all the same advantages CVMFS does with unpacked files as you get with CIF files and HPC. In addition, it has a bunch of other advantages. You get instant worldwide updates. So you publish a new file anywhere, the source of that repository is in the world, and they're immediately available on all the systems that are mounting it. You don't have to worry about copying your CIF files around to your HPC system you're working at. It's also, there's no need for set UID privileges to mount CIF files. So currently, it's still the case with Apptainer and Singularity. If you want to use CIF files, you need a set UID root installation. And we don't need that with CVMFS. We can run completely unprivileged using unprivileged user namespaces, because the sandbox format can run with unprivileged Singularity Apptainer. And there's also no need for the local high-speed file server now. You don't care about that in HPCs because you already have one. But high throughput computing on the grid world, all of our systems are just standard PCs, standard on rack mounted usually, but they don't have a shared high-speed file server where you can mount the file system. We have distributed file servers instead, and this is just excellent for that. It also scales to much larger application software bases, because like CMS and Atlas, this huge LHC collaborations that's based at CERN, they tried using CIF files. They had to in order to run on some HPC systems, and they would just naively take all their releases that they might want to use and try to put it into one container. And it would take about half a day to generate and end up with 200 gigabytes just to make the CIF file. And where we have all this stuff published already in CVMFS, it's all there. Anytime anybody needs it, you can just go and grab the piece you want. And it's also much more efficient storage due to file level deduplication. When you start making all these different containers, it turns out that you have a huge amount of same files. The vast majority of the files in each CIF container is shared, is the same one as in all the others. So it's much more efficient at storage due to files. So for example, and some of the Stratum ones, which has all the main repositories from CERN and Open Science Grid and from EGI, they're up to, I think, in the neighborhood of 20 terabytes after having been run for years and years and years. And this is because, and they have all those files that are published and they're all stored. It's really because of that deduplication and compression that's making that a really efficient storage. Also, CERN and OSG each have a repository that hosts they're shared for publishing containers specifically, Singularity containers, and they're both are updated automatically from Docker Hub or other container registries in the case of the CERN one. And so, well, using these shared repositories is the great advantage of deduplication of all these many common operating system files. So even different projects are all sharing these two repositories. They're almost all of them are based on EL7 hosts, right? So we end up sharing a whole lot of the files between the different repositories. This makes it much better for storage. It's also very convenient for updates because once you have your container registered in one of these repositories, then they automatically update whenever you do a Docker push. Docker push, you get a new version, then it'll automatically publish to CVMFS. So that makes it very convenient. And then now what you have in these repositories generally, in most cases, are only the base operating systems plus whatever package software that each project needs. So it's not the application software themselves. So it's these containers are actually not all that big, because all the application software, which is the big bulk of the software, is we instead install those in separate per project repositories. And then they can install however many releases that they want and all their other externals that they compile themselves and that aren't already in like RPMs. And later in this talk, as the last third of my talk is about, I'll be talking about plans for full application, including the user, the application software and user containers. We're talking also plans for distributing those in CVMFS. The CVMFS project itself includes a tool to manage these container repositories. It's used for unpacked.cern.ch. It's called CVMFS-duck. And OSG is actually not using that tool since they have their own called CNFS Singularity Sync, which predated CNFS Duck. Otherwise, if Duck was already there at the time, they probably would have used it. But meanwhile, they're still using that. But it basically does the same thing of publishing sandbox repositories automatically out of Docker Hub. So this is just a picture that I happen to have handy that for how that works. So first, the user makes a pull request or makes a ticket to register the container for those two repositories, and one of those two repositories, and then they put that in GitHub, and then this ends up then they what they do is a Docker build and push whenever they ever want to do an update. It gets automatically synced on the changes from there. This is it automatically, I think this part is it will automatically build Yeah, I'm not even sure what the picture is for. So anyway, it ends up automatically being available in CNFS and available to the world. So, all right. So I also want to talk some about using CVMFS and HPC. I think that may have also been covered some last year and the CVMFS talks. But CVMFS was designed for, and it's essential for high throughput computing. It really, it took off when it first became available. High throughput computing, it was like, oh, this is a no-brainer. We are obviously going to use this because that's what it was really designed for. And but it's also great for HPC, like all those reasons that I listed earlier. And now one issue that we have on HPCs often is that CVMFS requires a local cache, and a lot of times HPC nodes are diskless. I really wish that HPC designers would just put a little SSD on every along with every chip. They're trying to save a little bit of money. They say, we don't need this because we got a high-speed file system, but it's really, really helpful for a lot of things. And so there are many ways that people have come up with, CVMFS offers to deal with this, but the best one that I found for those system administrators who are willing to mount a separate loopback file system per node for that cache, and also for any local job scratch workspace. And so they allocate some space on the high-speed file server that's dedicated to one node, mount it with a loopback file system. And from then on, everything works just like it does in Singularity. We've got all the metadata operations are again moved back to the node. And that's what works great. Now, another issue that we have run into, this is not so much but in the past, we've not so much these days, but some system administrators are just suspicious of Fuse, and CVMFS is based on Fuse, file use, in user space, file system and user space. And then another big thing is that not all the HPC users need CVMFS, and system administrators are really hesitating to put any kind of reserve resources, something that's always installed and available, even if you're not using it. It does run a couple of processes, which when not using it, they don't take much, but they do take a little bit of memory. And you have that allocated cache space that, well, what if someone else wants to use that? So that's another thing that HPC system administrators are often leery about, but it's just because it wasn't invented there. So then the easiest and most robust way then to install CVMFS, well, first I was going to say, I really recommend, if you can install it normally, that's the way to go. If you can convince the system administrator, if you run the system, HPC system, install CVMFS. It's the easiest way, it's the most robust way, most reliable, and can use it for getting all your easy build packages, right, Kenneth? You have CVM packages built, distributed already in CVMFS, and all sorts of other advantages you can use independent of what whether or not you're running jobs from people traditionally used to running in high throughput computing. But when it's not possible, I have a package called cvmfs-exec that makes it as easy as possible to use CVMFS as an unprivileged user. And it has 4 different modes. I'm only going to really talk about one of them today. They all have caveats, and that's why I say it's easier, better to just install it as root in the normal package as you can. But if that's not possible, this third method with unprivileged user namespaces is really not that, it makes it as easy as possible. So, it depends on unprivileged user namespaces, including the third method includes also requiring unprivileged fuse mount. It's the one that works the best. It's the one I'm going to talk about here. And as long as you have RHEL 7.8 or later, you've got that. It's not enabled by default on RHEL 7. You got to enable it, but they're available and it works great. And and also if you have other, any other kernel, as long as it's got these features available. Okay, so here's an example way to use CNFS-exec in this mode 3 that I'm talking about. First, you run the command make this. This is a tool included in the package, and it will download all the CVMS RPMs and configuration that you need, and it will be sent to jobs. And this is example here. I'm gonna switch over to doing a live demo. Let's see this one here. So I'm here on a machine that does not have CVMFS. This is an EL7 machine, does not have CVMFS, does not have Apptainer. And I'm just going to copy and paste from the screen here. And you get to see what it does and get the output too. So it downloads all the CVMFS code itself. The CVMFS code itself is not that big. So that's 43 megabytes, and as well as the configuration. And now if I do this, it showed that it mounted /CVMFS those repositories as well as the configuration repository. Now here's the I have to, if you're doing this yourself, you got to copy paste this without the backslashes. Those backslashes I found got in the way. Here I'm running Apptainer, the latest, the first Apptainer pre-release out of CVMFS, and also running a container out of CVMFS. I messed up. What did I didn't copy paste entirely, right? Here we go. There we go. All right, now I got a Singularity prompt because this is an old container from Singularity instead of an Apptainer prompt, but I'm running this. This is now inside that container. I ran it with -C, so it's just those are the only processes running in it. So that's all it takes. If you have CVMFS, you don't even need CVMFS, just CVMFS-exec. You should be able to run this on your own machines. And it's easy. I'll switch back to a presentation. If you also then, I'm going to talk about the self-extracting distribution. So once you make this, that creates a directory called dist here. You can also create a self-extracting bundle with make this -o. And so it takes everything out of this directory and creates a file, which is executable. You can execute that and copy it wherever machine you want, and then run it, and it will automatically extract the CVMFS-exec, and so you can use it as if it is the CVMFS-exec command. It actually extracts all the software it needs, and then runs CVMFS-exec in there. So also, this is happening behind the scenes here. CVMFS requires a local Squid cache, right? I was talking about that. In order to work well at scale. But between the make this and make this -o, you can edit the CVMFS configuration to identify the Squid's location if you want. You know where it's going to be once you get there. You can edit and set up CVMFS configuration like normally. You say dist/etc/cvmfs is all the configuration. Or as the default configuration, which I used here, it uses the the WLCG, the Worldwide LHC Grids web proxy auto discovery servers at CERN and Fermilab. And it first looks for a server in your local domain space. If you have something called grid-wpad or something called wpad in your local domain DNS name, and then looks for a server there called wpad.dat. We'll use those first. If they're not found, it goes to a server at CERN or Fermilab. And then if those two servers will look up if squids are known to the WLCG based on where your IP address is, what you're doing the request from, those get returned. And if no squids are known, then it connects to Cloudflare aliases for those stratum ones and openhtc.io. If it also, in order to avoid abuse, if there's many requests coming from the same organization with no squid within 15 minutes, if there's lots of them within 15 minutes, then it ends up redirecting you to another, to backup proxies, backup squids at CERN and Fermilab, and those get monitored. And we can find out, oh, hey, we need to try to contact you we have an operations team that looks for these, and you say you need to install some squids locally, but this is good for relatively small numbers of, it'll just use the Cloudflare caches worldwide. Also, you can, if you use my Frontier Squid package, there's an option in it to automatically register itself with WLCG. So if you just set that extra option when you install your own squid, it'll register, and you don't even have to change the configuration of the in general of CVMFsexec or anybody else that's using this web proxy auto discovery. Now there are things, I see I'm getting close to my half hour, but I actually have more time, I think, so I'm gonna keep going. The cache has to be managed carefully with production use. That's something that you need to worry about with CVMFsexec. So by default, it allocates 4 gigabytes of space under its right there in its disk directory. Up to there, it will use for caching. But the problem is, if you are running multiple different jobs on the same machine, they really can't share the cache. So it works best if it's controlled by pilot jobs. I don't know if you're familiar with pilot jobs. We use these all the time in high throughput computing, where a project first sends in a job, and it then pulls in jobs from within the project. And so if these pilot jobs use CVMFsexec and try to use, as if you can use the whole node, then that's great. It can manage this cache, maybe give yourself more cache. Also, you need to avoid putting the cache on your home directory, or that's where your shared file system is, because you get back again to the high load on the metadata servers. All right, so now I'm going to talk about the last topic. This was about scaling up the number of containers in CVMFS. So we are currently manually registering containers for CVMFS distribution, but it's really designed for a small number of containers per project. So you have this small group of people who are the ones who maintain the distributions for your project, and then they can just put out the one per release, or even fewer than that. Because it's one per release, they need to have to go through and register each time they get a new release. However, there have been requests, there have been people wanting to scale this up so that you can have individual researchers within a project, each have their own container with their own analysis job. And so we've got a plan for this. We haven't implemented it yet, but all kinds of problems then result when you're new problems, right? So first of all, the time to publish these huge containers can be prohibitive, especially if it's got all the application software in it and a little bit of software from each researcher that's different. Also, the time to distribute these updates to stratum ones and clients really needs to be minimal if we want to be doing this all the time. And people are, every time they submit a batch of jobs, they want their container to be available soon. And they're doing it, multiple times a day, say, they're updating, trying new things. So also that means reliability needs to be much more critical, that we can't have like downtime on that one server for a day while you do an upgrade, because then people can't submit jobs at all that day. So this becomes their primary means of doing development. And then there's also a need to be able to clean up software that's no longer used by jobs. It needs to be automatic because they run a set of jobs and then they make new software and run another set of jobs. And we usually expect otherwise than when you have a small group of people maintaining software distributions that typically they just never delete any old things. But if they do want to clean up, then they do a manual process to do that. That's different in this case. So there is a new feature in CVMFS server in the latest release 2.90 that addresses the container publish time problem. So we assume a fully self-contained container is made up of many Docker layers, or at least, or even if it's a small number, some of them are going to be huge. And presumably almost all the files will be in layers shared with many members of a large project. So they have a particular release of all their software, but it's still very big. And so in this case, we don't have project software coming from different CVMFS repositories like we're doing now. So everything has to be in the container. So this new feature that's here, it enables a quick copy of only catalogs from one path to another. So we've got, let's say we have all the lower layers in one path. We're going to make a new copy, quick copy of it, and then you can just add on a small layer that's different. And so this, in any case, the files would be shared, even if you had to republish that whole long list, a whole big list of files, and it would end up finding, oh, this file already exists in the repository because of deduplication. But this avoids all the huge costly time you got to go through and process. So CVMFS publish command is to process each file, read them, create, compress them, figure out their hash, figure out where to store them. So that would all be avoided with this new feature. And Duck has been updated to detect when those layers are shared, and it will invoke this new feature. And then for the other issues that I talked about, I already have a package called CNFS User Pub that's used only at Fermilab so far that addresses the other issues, because that package currently, it publishes user software, only the user software piece, only the research we call user, that's the researchers, and it just puts them in as a tarball. So in CVMFS, so we have CNFS User Pub, but the user, whenever some users at Fermilab submit a job, they give a tarball of software they want to distribute. It goes over to this other servers that publish them in CVMFS. And we do reliability by having two publishing servers that will go in either one. If either one is up, it'll publish. And each of them has two CVMFS repositories. So that it ends up going in, it'll randomly go into one of 4 repositories. And then we have a job wrapper that comes and looks in all 4 repositories to try and find the user's code. And the reason we have 2 repositories in each publishing server is garbage collection. I haven't talked about that before, but in order to get rid of all these, in order for CVMFS to know when it can actually delete a file, it needs to go and scan all the catalogs in order to find out whether or not it's still referenced anywhere. It's really very much like garbage collection and object-oriented programming, and it's called garbage collection. But that takes a while to go through all that time. And we don't want to be able to block publishing entirely on one of these servers while garbage collection is happening. So that's why we have the second repository that it can go to while garbage collection is happening in one. And then we also minimize the distribution time in CVMFS by having the stratum ones treat these repositories specially. They go on a separate fast track from cron, and every minute it checks, instead of typically the other stratum ones, they check every 5 minutes, and they check one repository at a time. So it can take delays can happen depending on how big of a publish happens in some other repository in those cases. So and then the time between the clients checking is typically 4 minutes to check for a new update, and we reduce that down to 15 seconds. So the result is that updates are available on clients within a few minutes. And then it also has automatic deletion of publishes that haven't been used in 30 days. So my plan is to extend CNFS User Pub to publish containers, then using CNFS Duck as another option, so that then we'll be able to set up more servers for the and more repositories to publish those in. So that is it. And I have links for all the things I've talked about, most of them anyway, if you want to look up more. Questions?
Yes, if there are questions, then those of you in Zoom, raise your hand. Otherwise, particularly looking at several of those you've been talking on Slack, if you want to raise the question.
Hi Dave, thanks for the interesting talk. I was a bit curious about, well, one thing in particular about the CVMFS performance with MPI executables. So, right, so if you're running a large amount of nodes, and specifically I was wondering about jitter. So like you're running the service on each of the nodes and it's doing things in the background. So if anyone has looked at the impact of jitter in large jobs.
I haven't heard about it. I don't know if anybody else on the call today has tried that, but yeah. So it might affect your timing some because it has to the first time you access it. So I would assume that, you know, if you can set it up to preload everything by, you know, touching everything once, something that make sure that it's all there, but that once it's all loaded, it should then all, you know, not insert any more delays. You know, if you're not doing any more loading on your nodes, then it should be, there's nothing more slow that it needs to do. So.
Okay, so it doesn't periodically do any kind of checking or anything like that. It's silent unless you ask it to do something. Yeah,
I mean, there's, right. In fact, when you download something, it might fill up its cache and might need to do some extra work to delete things. But if you're done downloading anything and everything's already in the cache, there's nothing more happening.
Okay. I mean, I'll test it. I was just curious.
Yeah, try it out. Yeah. Go ahead, Bart.
Hi, just have a question about the diskless nodes. I know in Compute Canada we have one cluster that uses them as Niagara, and they use, to my knowledge, Alien Cache. So, do you know of any pros and cons of Alien Cache versus?
Oh yes,
the mountain?
CNFS Alien Cache. Yes, the problem with Alien Cache is it does not move the metadata operations. That's why I think you're going to be much better off performance if you do the loopback file system. So yeah, the alien cache is when CVMFS, it does not manage cleanup of the cache. It's just all the nodes point to the same path in a file system, right? And the shared file system. And then CVMFS will continue to download, and whichever one gets there. And actually, if two different nodes try to download at the same time, whichever one gets done first is the one that, I think, the one that stays there, or maybe it's whichever one's last. But anyways, they both download the same thing and they don't end up clashing. It works, but your performance isn't going to be as good as if you move the metadata operation, because then you still have all those zillions of files. They're now on a shared file server and all the nodes are trying to access it at once. So it's going to slow down in your metadata operations, you know, unless you've got not a very complex application. You're going to have better performance by, it'll probably take more space, but if you do the loopback file systems, but it's managed space too. That's another thing you need to worry about with the alien cache, is that the system administrator needs to occasionally delete stuff so that it doesn't keep on growing without bounds. But maybe they don't care about the space too, that sometimes they just let it grow. But
all right, thanks.
Dory's next on the hand raised. Oh, don't hear you. Don't hear you even though you're unmuted. So maybe you see you had your question in the chat.
Can you hear me now?
Yes, yes.
Okay, sorry about that. We are just starting to use CVMFS and EasyBuild. We're sort of modeling on what Compute Canada has. We're a smaller center. We have anywhere from 1,500 to 2,000 nodes at any given time. We're just curious if there are any recommendations on how many caching servers would be needed to support that. And also, I was a little bit concerned about you saying sharing cache on a node with the high throughput jobs doesn't always work. We do share, our jobs share nodes, so just wondering if that might be an issue for us.
Well, here I was talking about CVMFS-exec as far as sharing there. Is that so what you're referring to?
Oh, okay.
Yeah, about the cache considerations. That's CVMFS-exec. So if you've got a regular installed CVMFS, you're great. It's all shared. So you're asking how many Squid servers you would?
Yeah.
Yeah. Probably 2, because for reliability, when you have that many nodes, just having one is not a good idea, because just for reliability purposes, even if it's, I don't know if you monitor, we have a big monitoring system in place with WOCG, that all the sites, Squids, we ask them to register, and then we can watch if any performance. We also have a failover system. I don't think Compute Canada does, but if you're using any of the CERN or Open Science Grid or EGI repositories, those are all set up so that if your Squid fails for some reason, like if you only have one Squid and it goes down, all the jobs don't die. They start using Squids at CERN or Fermilab, and we get an alarm to show, and so we contact the sites to say, you got a problem with your Squid. But they do slow down because they all have to get all this, and they use a whole lot more network, a lot of small packets go, a lot of small requests going over the network, over the wide area network. So to avoid that with a large site with as many nodes as you've got, we would say you ought to have at least 2, and depending on it, a lot depends on how quickly jobs start, how much each job, you got to watch the monitoring to see whether or not you need a more powerful machine or not.
Okay, great, thank you, and thanks for all this information on Singularity with CVMFS too. That's very useful.
Yeah, and I also say that at CERN for CMS, I run the Squids there. We use 2 Squids, and we have I don't know, but probably 100,000 nodes, many tens of thousands of nodes anyway, and we use only 2 Squids, 10 gigabit, and it's able to handle all the load. That's one of the most heavily loaded systems around. So 2 Squids you can do pretty well as long as it has decent hardware behind it, and you might not need that much. You don't need as much probably as CERN does, as far as so we run like 6 Squid processes on each of those nodes. By default, Squid you only get 1, but at least the Frontier Squid package makes it easy to, and even regular Squid makes it easy to run multiple Squid processes on one machine. That's when it gets, the CPU becomes the bottleneck, when you get to the higher throughput on one machine. So Kenneth is next, raising hand.
Yes, I think there's actually maybe another question from Slack as well, but I'm happy to raise mine. So I was wondering if you've looked at security concerns in terms of ingesting stuff into CVMFS. So to what extent do you actually review what is ingested before you actually do that? Because as soon as you ingest something into CVMFS, it's really available on all systems where that repository is being mounted, and that seems like a very attractive attack surface for malicious people who want to get in, like a single binary that opens a backdoor or something like that.
Well, as far as, I mean, it's very robust security from publish time all the way to the end client node.
Yeah, that's clear. Yeah.
That's clear. So are you worried about someone who has the rights to publish might be ingesting
Yeah,
something?
it essentially trick people into ingesting a binary that has a backdoor. So unless you're really thoroughly reviewing, especially container images, because there could be thousands of files in there. Do you use any scanning tools to check those container images first before they get ingested or anything like this?
No. And the thing is, with unprivileged containers, unprivileged containers, there's very little damage that, almost all the, we got operating systems in here, and there's all of these CVEs from operating systems, but those are 99.9% anyway, don't affect application software. Those are operating system kernel things. So we don't worry about it. If it is like if we end up with library issues that can still be exploited when you're only doing outgoing connections, those are the 0.1% that we sometimes worry about, but they're really, really difficult to exploit. And so usually, haven't worried about it. So.
Yeah, so is it essentially because it's all in user land, really, it's not too big of a concern. Yeah.
Right.
Okay. Maybe we can also raise Thomas's question. I'm seeing it's being discussed in Slack as well, but he was wondering if people are using RAM disk as well for CVMFS caches as an alternative to a loopback file system.
Yes, that's one of the alternatives I didn't talk about, but
yeah,
if you don't mind using up, burning up the RAM, that does work as well.
But you typically don't need a lot of space, right? Like something like 10 or 20 gigabytes is already plenty, of course, depending on how much software you're actually pulling in. But
right,
since you're only pulling in files you're actually touching, which is probably a small percentage of a full container image, it's usually quite limited in terms of space you need.
I would say that I should also mention that the local node cache, things get uncompressed before they, so they are uncompressed there. They're on the Stratum 1s and the Squids, they're all compressed, but they get uncompressed once they get loaded into the local cache. Yeah.
Have you seen any numbers of how, let's say, what percentage of the volume of a container image actually typically gets used at runtime? Is that like 5-10%? Is it bigger? Of course, it depends on the workload, but
yeah, it depends on a lot of things. Yeah, I think I haven't done the measurements myself, but yeah, I mean, even all the operating system, even the operating system itself has all kinds of files that you're never going to use, right? And then the application software tends to be even at least as bad as far as all kinds of things that they might want to use sometime, but they're not using in this run. So yeah. But yeah, if you have multiple terabytes of RAM and you don't mind burning 10 gigabytes, you can do that. Yeah. But yeah, we've read other things like we run into system administrators of HPC systems. They don't want to put the CNFS software into RAM. It's going to be taking up space for everybody. That's only 42 megabytes. What are you talking about? Let alone the cache, Yeah.
Okay. Do we have any other questions, Simon? I don't think we have.
So Bart's showing there in Slack that if you do a DF on the CVMFS cache, it does show you the total size allocated. So that one has an 80 gigabyte one, but only 1.4 gigabyte was used. So yeah, I mean, it depends on your workload, and depends on if you're running lots of different jobs on the same node, then you need to allocate more. That's why I think 4 gigabytes may be enough for a typical single job flow.
Yeah, something like 80 gigabytes on disk is not a lot of disk space for the software installations. But actually stuff being used at runtime, that's quite a lot of stuff already. So you'd have to have a very diverse set of jobs to be able to fill that, I can imagine. Yeah. I guess we're good to wrap up here, Simon.
Yes, yes. Thank you to Dave for the talk.